Welcome to MasterCode. This is episode 1 of the ethical hacking series, Networking Deep Dive. Before you can hack anything, you need to understand how computers talk to each other. Networking is not just a beginner topic, it is the permanent foundation that every single skill in cybersecurity is built on top of. By the end of this episode, you will understand the OSI model, TCP and UDP, IP addresses, DNS, ports, HTTP, packet analysis with Wireshark, network scanning with Nmap, and how common network attacks actually work. Let us begin. Why does networking matter so much for ethical hacking? Every attack travels over a network. SQL injection payloads, phishing emails, malware downloads, data exfiltration, all of it passes through network protocols. If you do not understand the path, you cannot understand the attack. Every defensive tool is also built on network knowledge. Firewalls, intrusion detection systems, VPNs, and network segmentation all require deep understanding of how traffic flows. Reconnaissance and scanning, the very first steps of every penetration test, happen entirely at the network level. And since over 75% of bug bounty vulnerabilities are web application bugs, and web applications run on HTTP and HTTPS which are built on TCP/IP, networking knowledge is truly inescapable. Learn it well. Learn it once. Use it forever. Let us start with the big picture. How does data actually travel from your keyboard to a server on the other side of the world? When you type google.com into your browser and press enter, your browser creates an HTTP or HTTPS request. Your operating system wraps that request inside a TCP segment, assigns port 443 for HTTPS, and passes it to the network layer, which adds an IP header with source and destination addresses. Your router then forwards the packet across the internet, hopping through multiple intermediate routers. Eventually it reaches Google's server, which decodes every layer and sends a response back through the same process in reverse. This wrapping process, each layer adding its own header, is called encapsulation. And when the data arrives at the destination and each layer strips off its header, that is called decapsulation. Understanding this process is understanding what hackers intercept, inspect, and manipulate. The OSI model, Open Systems Interconnection, has 7 layers, and you absolutely must memorize them. Layer 7 is the application layer. This is what users interact with. HTTP, HTTPS, DNS, FTP, SSH, all application layer protocols. Layer 6 is presentation. This handles data format, encoding, and encryption. TLS and SSL live here. Layer 5 is session. This manages connections between applications, setup, maintenance, and teardown. Layer 4 is transport. TCP and UDP live here. This is where ports live, where reliability is managed, where end-to-end delivery happens. Layer 3 is network. IP addresses and routing live here. ICMP, the ping protocol, also lives here. Layer 2 is data link. MAC addresses and Ethernet frames live here. Switches operate at this layer. Layer 1 is physical. Cables, fiber optic, wireless radio waves, raw bits, the actual electrical and optical signals that carry everything else. The memory trick for the layers from physical to application: please do not throw sausage pizza away. Now the most important perspective, the OSI model from a hacker's point of view. Every single layer has its own class of attacks. At layer 7, the application layer, you find SQL injection, cross-site scripting, CSRF, directory traversal, and API abuse. This is where most bug bounty findings live. At layer 6, presentation, you find SSL stripping attacks and weak cipher exploitation. At layer 5, session, you find session hijacking and cookie theft. At layer 4, transport, you find TCP/SYN flood attacks for denial of service and port scanning. At layer 3, network, you find IP spoofing, ICMP floods, and routing attacks. At Layer 2, Data Link, you find ARP spoofing and MAC flooding. We will cover ARP spoofing in detail in this episode. At Layer 1, Physical, you find cable tapping, wireless signal jamming, and hardware keyloggers. When you approach a target, you are thinking about all 7 layers simultaneously. Where is the weak point? Which layer has the misconfiguration? This mental model makes you a better hacker. The TCP/IP model is the real-world implementation of networking, what the Internet actually uses today. It has 4 layers instead of 7. The application layer combines OSI layers 5, 6, and 7. Your browser, DNS resolver, email client, all application layer software. The transport layer is the same as OSI layer 4, TCP and UDP, ports, reliability. The Internet layer corresponds to OSI layer 3, IP addresses, routing, ICMP. The network access layer combines OSI layers 1 and 2, Ethernet, Wi-Fi, MAC addresses, the physical hardware. In day-to-day pentesting work, you think in TCP/IP terms. But when you interview for a security job or take a certification exam, you will be asked about the OSI model. Know both. The key practical insight: when you see a packet captured in Wireshark, you are seeing all 4 TCP/IP layers simultaneously, the Ethernet header, the IP header, the TCP header, and the application data, all stacked together. TCP and UDP are the 2 transport layer protocols, and understanding their differences is fundamental to network security. TCP, Transmission Control Protocol, is connection-oriented. Before any data is sent, the 2 parties perform the 3-way handshake, SYN, SYN-ACK, ACK. TCP guarantees that data arrives completely and in the correct order. If a packet is lost, TCP retransmits it automatically. This reliability comes at a cost. TCP has more overhead, which makes it slightly slower. HTTP, HTTPS, SSH, and FTP all use TCP because data integrity is critical. UDP, User Datagram Protocol, is connectionless. It sends packets without establishing a connection first and without any acknowledgement. If a packet is lost, UDP does not retransmit it. UDP is much faster, ideal for real-time applications like video streaming, online gaming, and DNS, where speed matters more than perfect reliability. From a security perspective, TCP/SYN scans are how Nmap identifies open ports. UDP is used in amplification attacks for DDoS. And the 3-way handshake is what makes TCP/SYN flood attacks possible. By sending thousands of SYN packets without completing the handshake, an attacker can exhaust a server's connection table. IP addresses are the logical addresses that identify every device on a network. IPv4 addresses consist of 4 numbers, called octets, each ranging from 0 to 255, separated by dots. Under the hood, each octet is 8 bits, making IPv4 a 32-bit address with approximately 4.3 billion possible addresses. The most important distinction for hackers is between public and private IP addresses. Private addresses, defined in RFC 1918, are the 10-dot range, the 172.16 through 31 range, and the 192.168 range. These are used inside private networks like homes and offices and are not routable on the public internet. Public addresses are everything else, globally unique and routable. Why does this matter for hacking? When you find a private IP address leaking in a web application response, like 10.something or 192.168.something, that is a significant information disclosure finding. It reveals internal network topology. IPv6 uses 128 bits and a completely different format. Always check for IPv6 during reconnaissance. Many organizations configure it improperly. Subnetting is how networks are divided into smaller, more manageable segments. The CIDR notation, classless interdomain routing, describes both a network address and its size with a slash followed by a number. The most common subnet in home and small office networks is /24, written as 192.168.1.0/24. This gives you 254 usable host addresses. The slash number tells you how many bits are used for the network portion. The remaining bits are available for hosts. A /16 gives 65,000 hosts. A /30 gives only 2 hosts, used for point-to-point links between routers. As a hacker, you use subnetting constantly. When Nmap scans a range like 192.168.1.0/24, it is scanning all 254 addresses in that subnet. Bug bounty programs often define scope as an IP range in CIDR notation. After compromising a machine on an internal network, you scan the entire internal subnet to find other targets. This is called pivoting. DNS, the domain name system, is one of the most important protocols to understand for both hacking and defense. It is literally the phone book of the Internet, translating human-readable domain names like google.com into IP addresses like 142.250. The resolution process works like this: when you type a domain, your computer first checks its local DNS cache. If the answer is not there, it asks your local DNS resolver, usually your router or ISP. The resolver then queries a root DNS server, which points to the top-level domain server for .com, the TLD server points to the authoritative name server for the specific domain. The authoritative server finally returns the IP address. For hackers, DNS is a goldmine of intelligence. The A record maps a domain to an IPv4 address. The name record is an alias pointing to another domain. Misconfigured names lead to subdomain takeover vulnerabilities. TXT records often contain SPF configuration, DKIM keys, and sometimes accidentally leaked API keys or internal information. MX records reveal email infrastructure. And NS records identify the authoritative name servers, useful for attempting DNS zone transfers, which can dump the entire DNS database of a domain. Ports are virtual communication endpoints on a device. Every network service listens on a specific port number, and knowing these numbers by memory is essential for any ethical hacker. Port 20 and 21 are FTP, File Transfer Protocol. FTP sends data including credentials in plain text, always check for anonymous login. Port 22 is SSH, Secure Shell. The primary way to remotely access Linux systems securely. Weak passwords or old versions are common vulnerabilities. Port 23 is Telnet. Like SSH but completely unencrypted. If you find Telnet open on a target, that is a critical finding. Port 25 is SMTP, email sending. Often open and sometimes misconfigured. Port 53 is DNS, both UDP and TCP. Port 80 is HTTP and port 443 is HTTPS, the web. Port 445 is SMB, server message block, Windows file sharing. This is where Eternal Blue lives, the exploit behind WannaCry. If you find port 445 exposed to the Internet, that is a critical vulnerability. Port 3306 is MySQL. A database port open externally is almost always a critical bug. Port 3389 is RDP, Windows Remote Desktop. A very common attack target. When you run Nmap on a target, every open port is a door. Every door needs to be tested. HTTP is the foundation of the web, and understanding its anatomy makes you a much better web application security tester. Every HTTP interaction has two parts, a request from the client and a response from the server. The request starts with the method, get to retrieve data, post to send data, put to update, delete to remove. Then comes the path, the HTTP version, and the headers. The headers are where things get interesting for hackers. The host header identifies which website is being requested on a shared server. The cookie header carries session tokens. The user agent identifies the browser, and can be modified to test for injection points. The response also starts with headers. The server header and X powered by header reveal technology versions, search those versions for CVEs immediately. The setCookie header creates session cookies. The critical difference between HTTP and HTTPS, HTTP sends everything in plain text, any device on the network path can read it. HTTPS encrypts the traffic using TLS, so only the client and server can read the content. As a penetration tester, you look for missing security headers, server version disclosure in response headers, cookies without the secure flag being sent over HTTP, and login forms that submit over plain HTTP. Nmap, the network mapper, is the first tool you run on every authorized target. It is essential. The basic Nmap scan uses -SV for version detection and -SC to run default scripts. This gives you a clear picture of every open port and what service is running on it. For a comprehensive scan of all 65,535 ports, use -P with the minimum rate flag to control speed. The aggressive scan with -A combines version detection, default scripts, OS detection, and traceroute. It is very noisy, only use it in authorized environments or CTF labs. Nmap also has over 600 scripting engine scripts for specific tests. You can scan for specific vulnerabilities like Eternal Blue on SMB, enumerate HTTP directories, test for default credentials, and much more. Always save your Nmap output using -ON for normal text format. As you progress in cybersecurity, you will run thousands of Nmap scans. Keeping organized output files is a professional habit that separates good pentesters from great ones. Important, always verify you have authorization before running Nmap against any target. Port scanning unauthorized systems is illegal in most jurisdictions. Wireshark is the most powerful packet analysis tool in existence, and spending time with it will teach you more about networking than months of reading. When you open Wireshark and start a capture, you see every single packet flowing through your network interface in real time. Wireshark automatically identifies over 2,000 protocols and breaks each packet down into its individual fields: the Ethernet header, the IP header. ARP, Address Resolution Protocol, operates at Layer 2 and is responsible for mapping IP addresses to MAC addresses on a local network. When your computer wants to send data to another device on the same network, it knows the IP address but needs the MAC address to construct the Ethernet frame. It broadcasts an ARP request asking, "Who has this IP address?" The device with that IP responds with its MAC address. Your computer caches this mapping in its ARP table. The critical security weakness: ARP has no authentication. Any device on the network can send a fake ARP reply claiming to be any IP address. This is ARP spoofing, and it is the foundation of man-in-the-middle attacks on local networks. Here is how ARP spoofing works in an authorized penetration test. The attacker sends fake ARP replies to the victim: "I am the gateway, my MAC address is this," attacker's MAC. And sends fake ARP replies to the gateway: "I am the victim, my MAC address is this," attacker's MAC. Now all traffic between the victim and the gateway flows through the attacker's machine. The attacker can read, modify, and re-forward every packet. This is a complete man-in-the-middle position. Defenses include dynamic ARP inspection on managed switches, which validates ARP packets against a trusted database, and static ARP entries for critical infrastructure like default gateways. Let us cover 4 more common network attacks that every ethical hacker encounters. DNS cache poisoning: an attacker injects false DNS records into a resolver's cache. The next time any user queries that resolver for the poisoned domain, they receive the attacker's IP address instead of the legitimate one and are redirected to a fake website. DNSSEC was designed to prevent this, but many domains still do not implement it. Man-in-the-middle attacks place the attacker between two communicating parties. ARP spoofing is the most common local network MITM technique. On public networks, rogue access points, fake Wi-Fi hotspots, are used. SSL stripping downgrades HTTPS connections to HTTP. Defenses include HTTPS with HSTS headers, certificate pinning, and using a VPN. Packet sniffing is passive, the attacker captures traffic without injecting anything. On unencrypted networks or after a successful MITM attack, all plaintext data including credentials is visible. Wireshark and TKDump are the primary tools. Port scanning, the most fundamental recon technique, discovers which services are exposed. Nmap identifies open, closed, and filtered port states. Every open port is a potential attack vector. Always use these tools only on systems you are authorized to test. Before you move to the next episode, you must complete these hands-on labs. Reading is not enough. You have to practice. Lab 1, Wireshark Packet Capture. Open Wireshark on your Kali Linux VM, start a capture, and browse to http://neversSL.com, an intentionally non-HTTPS site. Filter for HTTP and follow the TCP stream. See your own browser requests in plain text. This experience will permanently change how you think about unencrypted web traffic. Lab 2, Nmap Network Discovery. Scan your home network using map-sn followed by your network range. Find all live hosts. Pick one and run a full version scan. Read every open port and service version. Save the output to a text file. Lab 3, DNS Reconnaissance. Use the dig command to query a records, MX records, and TXT records for several domains. Compare what information is exposed publicly. Try querying different DNS servers and compare results. Lab 4, go to tryhackme.com and complete the free rooms in the Network Fundamentals section. The rooms on packets and frames, the OSI model, and extending the network will reinforce everything covered in this episode with interactive, hands-on exercises. Do all 4 labs before moving to episode 2. This is not optional. Here are the best free resources to continue your networking education after this episode. Professor Messer's CompTIA Network Plus course is completely free on YouTube. Search for it by name. It is the most thorough and clear free networking course available, and it covers everything in this episode in even greater depth. TryHackMe's Network Fundamentals Learning Path has free rooms on packets and frames, the OSI model, and network services. All browser-based with no setup required. Cisco Networking Academy at netacad.com offers free foundational networking courses backed by one of the world's largest networking companies. Wireshark with the Packet Life cheat sheets is your daily practice tool. Download the filter reference from packetlife.net and keep it open while you practice captures. The CompTIA Network Plus certification is an optional but valuable credential that proves your networking knowledge to employers. If you plan to work in cybersecurity professionally, it is worth considering. And most importantly, your next step is Episode 2, Operating Systems for Hackers. We will cover Windows and Linux internals, processes and memory, file permissions, the registry, and how hackers exploit operating system misconfigurations. You have completed Episode 1, Networking Deep Dive. You now understand how data travels through a network. You know all 7 layers of the OSI model and their corresponding attacks. You understand TCP versus UDP and the 3-way handshake. You can read IP addresses, work with CIDR subnets, and perform DNS reconnaissance. You know the critical port numbers by memory. You understand HTTP and HTTPS request and response anatomy. You can run map scans and analyze packets with Wireshark. And you understand how ARP spoofing, DNS poisoning, man-in-the-middle attacks, and packet sniffing actually work. This knowledge is the permanent foundation of everything that comes next. Complete the 4 hands-on labs. Spend time with Wireshark, capture your own traffic, follow TCP streams, see DNS queries resolve in real time. Run map against your own home network. These practical exercises are what transform concepts into instinct. Episode 2, Operating Systems for Hackers, is coming next. Subscribe and turn on notifications so you do not miss it. From MasterCode, keep going. You are building something real.